So like it's too much to do, so I have like I'm back here reaching out.
I think that's exactly how I think. So that's why all of the time slots are because they have.
It's like weird to think about how like
Yeah. So I don't know if I'm much as I know, but it's my time. I think so.
yeah, I just
But they're seniors. So
see everyone who's like it's like I have to go to the one day.
Those are so good. I can see those very like.
Yeah, it's like
Yeah.
I want to work starts drive like after my own income. So like my mom paid off for Thanksgiving.
And then turn that way.
I don't like after effects. It's broke the church.
Yeah, are you going to the band tonight?
I wish they just said that. I'm glad that things happen.
I know.
So I wanted to go to but why are we just
I have tickets, but I just
I can't
play because
I have so much to do. I like would not go. Like Microtubules.
Yeah.
I have a lot. Like,
All right, guys, let's get started. We're just missing Anne.
I think you're gonna go. It's so hard.
All right, so stuff I'm gonna catch up on. I started grading the midterms already. I'm like past the vocabulary and like halfway through page one. A lot better than the first midterm in the vocabulary sense, but there's still a few that I got with some of the keywords. In the front part, some of them, there was a typo on one of the questions. If you got that one wrong, when you get to midterm back, if you can argue it, I'll give you the full credit for it. Right? So you just come to office hours and argue it, and then you get the full credit for it. I'm not gonna say which ones, you guys have to find out. And if you do know, don't share it.
If it was a typo, do you mean argue like the correct version of the question, or why we put the answer we put?
So it's like if the typo threw you off, right? Then you might have picked one answer instead of the other, right? So if that's the case, it's like you might have picked this one instead of this one. Go back, argue the typo, and you know that's what made you pick the wrong answer, right? So it should be like between two options. I don't want to give it away. Let's get the difference back to you guys. You'll see it should be quick. I'm gonna try rushing them as much as I can. Because that being said, so I'm still thinking about the final thing. I gotta think about how I'm gonna make the last set of the exams, right? It's 2 hours in class time, but I'm not sure if, I wanna see how you guys do here first to see how well I can, I'm gonna write it, because when you guys have the exams in class with no notes, like I have to make sure my questions can't be too in-depth or too specific about specific knowledge. Normally those midterms, I go a little bit easier on my questions. As you guys saw today, this is an at-home test. It's like, hey, you better know all the pathways. Like you have no excuse. I can ask you, go up and down a pathway, cross a pathway, compare two things. And because you're at home, you have all this time, I can have all the fun that I want, right? So with that being said, it's like, let me see how the grades go. We'll talk about the final, whether we'll do, again, one of these 24-hour exams or we do in class. I'll make it the same size, aiming for you guys to finish it in an hour. But I will give you the 2 hours with no notes. You guys just come to the class, take you 2 hours, and then you guys are done when you're done. Yeah, so then we finish grading and we'll talk about that. With that being said, someone, you gave me the question about, you're like, hey, if you already have three good grades and you're cool with it, can you just not take the final, right? Technically, the answer would, right now feels like yes, but I'm scared for you guys. Just being, you know what, I'm not gonna do the fourth section of the exam at all. So right now, the only thing I'm thinking in my head is like, as long as you get a minimum a D on the final, I'll let the other stuff fly. That's my current thinking, right? So that way I'm gonna at least try, come to class, listen to the stuff, get an understanding of it. I just don't want you guys to just completely drop the ball in the fourth section and be like, I'm gonna ignore it. Right? So you get a D on the final, you know, just at least try, then I'll be happy with dropping the grades. Yeah. What else was I gonna say? We have that, the paper. I dropped the ball on that one. That's my bad, you guys. So I went to go check, and it was I think on Friday we glanced at them. I only put a few into a folder. Some of them I didn't pick your final one, so I just barely did it last night. So that means that the third research article, you guys haven't had time to do it. So I'm thinking, you guys okay with the deadline being Friday, or should we? You can push it to Monday if you guys need to, and I'll take over a little bit of your weekend if you guys don't mind. Let's do that Monday. All right, so I'll move it to Monday. And then again, share it on Google Docs, type everything into Google Docs. Do not use AI. If you use AI against me, I will report it to the honor code. Okay? Read the papers, feel comfortable. And then I think we're gonna do one last paper together where the whole class is only gonna do one paper, but I'm really gonna go into the methods, right? Because I want you guys to leave here kind of powerful, like in the sense of how we can really shred a paper and get as much data out of it and really understand what we're trying to solve. Yeah. So the last one, we'll do it together, the write-up for that one. I'll see how I feel. I might not have you guys do it. I might have you guys do like, I'll modify it, but it's gonna be more like, can you really pull out how a method, based on what it can measure, really give you information. Once I pick it, it'll make a little bit more sense to you guys. All right, so let's get into today's stuff.
Have it be like another point booster.
What happened?
Have it be like another point booster.
That's what I'm thinking.
Kind of
something
like
that.
with the epinephrine signaling and the group assignment stuff.
Yeah, so then with that, it's like I have my other class at 243, which is the like molecular methods. And in that class, what we do is we grab papers like this and we kind of dive deep into the methods in the class, like research is each different topic. And then as a group, we bring all the info together. So I might do something like that, and then like whoever contributes, I'll shower you guys with points for that. You know what I mean? Like I'll give you extra points in your class. Yeah.
Are we still able to do like the 25-point extra credit thing? Is that?
Absolutely, yeah. I'm hoping everyone's gonna do that, right? Yeah. So remember, it's 25 points if you do it either something with Swan, right? So if you're involved in a club, an organization, sports, events, write it in. Right? Just give me the connection of something to class. It's open to any sections. For example, what was it? I think I was talking to Izzo, right? Izzo is athlete. She goes and talks about, hey, how her system basically when she's running around, she's dropping her ATP levels, crazy amount of AMP. She's gonna activate AMPK. AMPK will do the signaling. She explained that's happening while she's running around. She's not making glucose, but she's breaking down glycogen. Perfect, right? So it'll be a boost of the activity you do, something connected to Swanee. So orgs, if you're part of them, cool. If you attend an event, I'll take it as well. Right? I think someone over here is doing a band, like the people see Swanee band. Write it in. 1 or 2 pages, just a quick thing, connect it back to class, and I'm cool. Sounds good? Yeah?
Yeah.
Do you want like a write-up or?
So here where I opened it to be as creative as you want. I'll take a picture, I'll take a diagram. Last time we did videos, like we basically did like a 2-3 minutes. Yeah, that's easy. Not very funny, guys. Yeah, so the videos, they were like we would like put their sense of humor into them, so we have some solutions. But yeah, you can do a video again, do your Swanee activity, and then connect it to the class, and then have fun with it.
Is there like a grading rubric that you're gonna post for it, or is it just kind of?
You're probably gonna get an A. That's the rubric. I can put it on there, but again, connect it to something in the class. The more, if you turn it in, you're probably gonna get a 25. If you give me something like, hey, you showed like something really cool, I'll throw some more on top. Everyone's cool with that? Yeah. Right. Karen, what's up?
you want this to be individual or a group?
I prefer individual, but if you do groups, that means you have to do a little bit more.
Okay.
Right, so if you're gonna paint something, then you're gonna paint something a little bit. If you're gonna do a video, add a minute or two for, for the person to do.
So then you said it's, so like 25 plus points, is that just like added on to like the final and it's like not counted as part of the class? Like if the class is out of 350 and we have a 300, it would boost us to a 325 out of 350?
Yeah. Okay. So it's gonna be good. Again, this is like, hey, we're a small community, we have to do a lot of work to make stuff happen, right? And this is one part where I'm like, hey, I can give you guys, cool stuff for being active. Yeah, so should be good. Have fun with it. Artistic, but connected to class, that way I can, I'll feel better. All right, any more questions? Wait, Emma, you had one, right?
Oh, mine was just if it was individual or if we could work with someone, if we did a really good job.
Do a good job, group, I'll take it.
When is it due by, just like the end of?
What is it? I'm to turn in the grades like a week after final, so try to get it to me around the final time. Yeah. I think my deadline is like the Tuesday after all you guys' finals.
Big May 7th.
It's like May 7th, so. At the end, I might start nagging you if you don't have it, just be like, hey, send it to me, send me something.
Yeah.
You can do cool stuff too, you can interview with the other bio professors, talk to them about something, I'll take it, All right. So let's do today's stuff and then, yeah, this should be, it's a fun day. All right, so we're working with microtubules. These guys are super beautiful, they're super dynamic. We're gonna have to watch a few videos to kind of get a sense of them, but then I'm gonna show you guys my little rough drawing of how I want you guys to kind of think about it. All right. So they're a super useful tool, they're a big part of our cytoskeleton, right? So that's what's basically giving us the shape to our cells. This picture, here we're looking at them as the green ones. And in this case, when we get into how they work, we're gonna see things that matter is their structural shape, like how they actually shape themselves. Because they look like straws, they basically have this really cool thing where they're really good at taking compression, right? They can bend a little bit here or there, they won't be perfect, they'll be a little flimsy, but when it comes to this kind of compression, they're very powerful in this axis, right? The other thing about them is they're very easy to build, they're also very easy to take apart. That's also a super critical tool. As you guys remember, when we're going to cell division, these are the big key players that help set up the kinetophores to grab onto those chromosomes, push things apart. If you guys go back to, I think it was the beginning of this class, Bio 133, remember the microtubules also basically have these little train tracks where we can carry our vesicles across this area, right? So we have a lot of tasks going on. What else? All right, so let's get a little bit into them. So again, when we're talking about the cytoskeleton, these things are very dynamic. In the cases of like, I think, what was it like, phagocytes use them for like when they're trying to chase down a bacteria, literally the cell's moving around, changing its shape. It has like a leading edge, it has a back tail. The microtubules are helping push that structure forward, gives it the shape. By using it, you can basically set something to go in one direction, you mess with the dynamics, you can throw them into a completely different direction. And it does it very, very fast. I'm gonna show you some really cool videos today. And normally the way that we're doing this is that we're kind of working on, like, we have these receptors that are sitting on that plasma membrane, just waiting to get the signal. And just kind of how we talked about the last section. That thing's kind of sitting on the membrane, the ligand binds, the signal gets internalized, and in here, we basically can regulate which proteins can help the microtubules. For today's lecture, we're going to talk about basically 3 different types of microtubule proteins, and I kind of go into detail about how they help out. All right, so to put it into the context of things, remember that there's 3 different types of cytoskeleton elements. We have the microfilaments, microtubules, and then the intermediate. I don't like these that much, I rarely talk about them, but these 2 are some of my favorites. In this case, I like to think first about what's their structural shape, because it really tells you about the jobs they can do. Again, microtubules, the way I remember them is, they basically look like straws, right? So imagine right here, we took Emma's coffee, she has a straw in it, right? If you push on the straw like this, you can see the straw will actually poke into your hand, right? So structures, it's really good at compression, like you can fight that back. Opposite to that, microfilaments, you can see it's basically a chain of 2 of them next to each other. So this thing, it's easy to compress it, but what it's really actually good at that one is putting, like, has like like imagine like a rope, like a twine, like intertwined rope. You can kind of pull on it, and that's where it has like a lot of its power. Intermediate filaments. One of this one we're talking about like shaping like the nucleus and all that stuff, but those two are the big key ones we're going to talk about today. All right, let me do this.
You said that the actin is good at pulling.
They're good at pulling, yeah. Because they'll be like they'll dimerize into each other, so it's kind of flexible and it kind of pulls on the, like you can pull them together by grabbing. Let's see how I explain it. Like you normally grab onto two molecules and they're connected somewhere else. You kind of pull them together. By doing that, you'll kind of tug at the
Tighten the rope.
tighten the rope basically. Let's get an example. Never mind. But if we look at them here, you can kind of see based on the arrangement, like these guys, normally they'll be pushing, like they'll try to push that plasma membrane and they'll deform it to make it stretch out. While in this case, you can have some of the actin kind of anchored on this side. You have actin anchored on this side, and there'll be like two cable strands hanging out like that. And then those cables actually get pulled together, and that's what's going to make this thing try to compress into itself. So let's check out that video. So this is how it can do that power. The cool thing about it is it switches jobs.
Microtubules are one of three principal components of the cytoskeleton. A microtubule is composed of tubulin dimers, consisting of two closely related polypeptides called alpha and beta tubulin. Tubulin dimers polymerize into protofilaments assembled around a hollow core. Tubulin dimers polymerize at the plus end of a microtubule. The polymerized tubulin dimers form a sheet that zips up into the mature microtubule just behind the region of growth. The tubulin dimers that add to the microtubule are bound to GTP. The tip of the microtubule contains tubulin dimers that are also bound to GTP. The rest of the microtubule consists of tubulin bound to GDP. Shortly after new tubulin dimers are added to the microtubule, GTP is hydrolyzed to GDP. The hydrolysis of GTP follows the growth of the microtubule. If the concentration of GTP-bound tubulin decreases, new subunits are added more slowly, and GTP hydrolysis catches up to the end of the microtubule. GDP-bound tubulin has a weaker binding affinity for its neighboring molecules than GTP-bound tubulin does, and the presence of GDP-bound tubulin at the end of the microtubule leads to its disassembly and shrinkage. The alternation between cycles of growth and shrinkage is called dynamic instability.
All right, so if we zoom into one of these molecules, this will be the two parts of that protein. They both bind to GTP, but the beta subunit is the one that we're going to care about, right? So this is the one that we can find it as a GTP, or it gets hydrolyzed and it becomes our GDP, right? So we'll be switching between the two states. Whenever you see GTP on this guy, it changes the conformation just enough that it fits happily to build the straw, and that straw is basically stable, right? So that's when they were kind of showing us in this part, my computer. Yeah, this perfect part. As we're building it, everything coming in has to be GTP bound, so to be right, you can kind of basically nestle into each other and build that really strong straw for us, right? As you're building something, you basically start using these guys up, bring them into your tube. Eventually, if you have all of them there, you're gonna have like that GDP wave kicking in. So let's say we started the cable, this will be a wave of tubulin being added, right? This will be the next wave, this will be GDP, GDP. GTP as we're adding, them, so we say GTP. It's totally fine, right T's for now, right? As time goes by, this is basically hydrolyzing stuff slowly. This is going from GTP to GDP, moving forward, right? If we just keep adding tubulin in GTP, we can technically have this reaction go on forever, it'll keep going, right? If we then are doing this thing, but then we run out of the free GTP, this last one, this process is still moving forward, it'll get to the last one. Now that that last edge is at a GDP format, that thing is unstable, right? And that's when it'll open up, flare up, and it'll start basically breaking this thing and releasing all these GDP molecules. The GDP has to go get recharged with a brand new GDP, and technically we can build it. Right? So things that we can use to work with this is here in the front part of the cable, basically. Here you have a faster dynamic of things growing onto it, but they're also very easy for them to get hydrolyzed to GDP, and that thing will fall apart on us, right? It's so as long as we have control over this, we can really change how this molecule behaves, right? In cell division, we talked a lot about this side. It's like, hey, if we play with this side, how we hold on the base, we can protect it on the centrosome, and that'll basically kind of hold it. So at this point, isn't trying to do that shredding aspect. Yeah. Let's go back. All right, so for this one, we're zooming in, right? We're looking at that cable. Like I said before, the tubulin, it has those two subunits, beta and alpha. I love to put this question on to trick people. And then they both bind to GTP, right? But it's only the beta subunit that does that hydrolysis, right? So when this changes from GTP to GDP, that's how we know that it wants to be in the cable. If this is at the front end, the cable's building, everything's great. If it gets hydrolyzed and becomes GDP, that thing's gonna fall apart on us and it's gonna fall right back, right? And decay into itself. So both are GDP prime burning, but this is the critical one. All right. Where's this cool video? All right, let me walk through the slides and then I'm gonna show you guys the video and then we're gonna kind of keep track of it. It's gonna look pretty cool. All right, so here they're going really into details. I'm gonna do that GCP, T's and D's, right? But here you can see this is technically a growing chain. You can see we still have that GTP sitting at the front. So it means that technically that last ring is stable. Doesn't matter how long this is, if they're GTPs, we really don't care, right? As long as the leading edge has GTP, that'll be the cap that basically keeps this thing stable. Yeah. If that eventually gets hydrolyzed, that's when we gotta start freaking out, right? If that last ring fails, it'll basically just start falling apart and shred on itself. You can see it releases the molecules, right? If that's the case, that's how we get the shrinkage. In order to keep having growth happen, we have to consistently bringing in the new GTPs, right? As long as they keep showing up, we should be all right. It'll be either, normally it's like if you're trying to build this cable, if another cable nearby fails and that GTP releases all those molecules, we can replenish them. Those GDPs switch out to a brand new GTP, and you basically can enrich this population. So by breaking one cable, you can release molecules to support another cable. Yeah. So this thing isn't just randomly growing and breaking, growing and breaking. There's other proteins that kind of come in and kind of help us refine or make this thing a little bit more precise. So for this, we're going to be talking about 3 different kind of groups, right? So first, we're going to be talking about polymerases. These are the ones that are going to be positive factors, helping this thing move forward so we can stabilize it. So in this case, it's like you can see it there, it's binding at the positive end. And they can help with like recruitment, or they increase the affinity of bringing in the GTP molecules to that site, right? So again, if the amount of GTP tubulin that we have determines how fast we can grow. Having something helping us bring these molecules in and put them on that site is gonna speed up this reaction. Right? The other one is, when we have the ones that depolymerize, these can work by almost acting like a gap. Some of them, what they'll do is they'll speed up that hydrolysis reaction, right? So what's gonna happen, our cool front that everything was growing to have GTPs, we start getting them to get rid of the phosphate, right? And they're getting hydrolyzed and becoming GTPs. We get GTPs at the front, cable's unstable, it's gonna fall apart in this. Right? Normally what's gonna happen is upstream signals would say something like, if we want the microtubules to push us in that direction, let's say a ligand outside comes in, hits a receptor, the receptor signals down, and it gets this guy to work at higher levels, right? And that's how on that side of the cell, boom, we're gonna be polymerizing microtubules to be growing on that side. On the other side, what we end up having is you end up building up these guys. If the polymerase builds up on the opposite side, we're gonna be shredding our GTP, so it falls apart on the old cables, and we're making our new cables moving forward. So these are really cool of like, if you localize these two factors, you can really tell a cell where to make cables and where to we can clean up the old ones. In that sense, this is the class ones, they basically kind of build a ring around it. And the goal with them is that, again, once our cable goes into that GDP state, it technically wants to just fall apart. And it should go from that plus end, it'll collapse all the way through it, shredding itself. These clasps basically are like a little ring that kind of helps hold it in place. That thing where the tubulin is trying to pop out, it counteracts it, holds the front. As long as you have the front stable, it's not gonna keep collapsing. So that gives us a little bit of like, if it's dynamic, it collapses, it only collapses so far, and then we can reset from that like starting site. So once the GDP comes back, then we can reset that tubule. Now check this one out. So in this case, the white parts, we're looking at a cell, and these white parts are representing a cap protein. So this one actually sticks. Like if we have I'm gonna work on the representation of the cable, like that. So this protein basically sticks at the 5' cap, like it stays on the cable. If the cable grows, it kind of goes with it like this. The thing is, in this video, you won't see any part of the cable, you just see the cap kind of migrating with it. So check this out. Look how fast this thing is going. So you can see we're kind of leaving our nucleus. From here, we're setting up, these are microtubules that we can set up from the center, setting up that cell. In some of these places, you can see this left, top left, you're probably trying to make something that kind of pushes out or protrudes. You're gonna load it up, you're gonna send a lot of microtubules in that direction, like that.
So the glowing part is the clasp, or is like the new part of this tubule that's been built?
Yeah, it's just a cap. So it's like we can't technically see
The GTP cap?
it's sticking right to the front of that cap. So it's like as you're building that straw, we're just basically keeping track of where the tip of the straw is. We're losing the rest of it. But in theory, remember that
It's still there.
plus end is where you have the fastest collapse and creation. If this thing is still growing, there should be a cable here of like that tubulin just closed up, ready to go in that direction. And some of them, you'll see that they don't make it all the way to the direction, they kind of like fade away. In those cases, we could be having those instability, right? They use the cap, they become unstable, and they'll collapse. And we'll recycle these to support the main cable.
Okay.
So see some of these guys out here are collapsing. I think they're gonna be some of the waste ones, but these are the critical ones. Now this is a different dye. So in this case, we have GFP on tubulin itself, and now we can actually see every single one of these guys. Right? So we're looking at the whole cable itself. Let's check out this now. See if I can isolate one. Wait till it zooms in. You can kind of see some of these cables being formed, like they're stretching, trying to grow, and they collapse back, right? It grows and collapses back, grows and collapses back, right? This is kind of its way of expanding. And some mechanisms, they'll have, like they still think they're in the right area trying to set themselves up. That's where the class helps. They'll try to grow. If they collapse, they only collapse back to the class. We can still try to reset that signaling. The other one is sometimes this positive end, the one that's dynamic, you can also capture it. If you trap that, you've basically made it stable forever, right? And that's the one that we really use for like our kinetic cores, right? That one, it's like, hey, we're using these cables to grab onto the chromosome. We're trying to pull them apart. The last thing you would want is halfway through cell division, your microtubules to fall apart and your DNA to be left in the middle, right? So at that point, it's like, if you protect the cross end, by protecting that cap site, you won't let it collapse on itself. You'll keep that nice stable cable. Well, we can do that type of mechanisms with connecting our microtubules even to like the plasma membrane itself. There are proteins that can catch it and they'll basically grab on really tight.
So it's still growing but slower?
When you, with some cap proteins, you can help them, it can help them grow faster. Some of them, it can still grow, it'll be slower, but in other ones, it'll literally be like, it will stop growing, it's just like it got captured. And again, if it can only fall apart from that top part of the straw, if you cap it, it's not going anywhere like that. That's a permanent microtubule. It's hard to get it to collapse on the inside. You normally have to bring in like extra proteins that they really work on just going in and cutting the microtubule like this way, like right in the middle of the reaction. Those are a little bit harder. Because you have to break. What is it? Like this is a cross section of this thing, right? When they want to break like a microtubule like that and just put it apart, you have to imagine all these protein interactions that are sitting grabbing onto each other. You have to break literally all of them, and they're correlated to each other, so you're gonna break it in the middle. But once the front end falls apart, it'll be like the moment this one's gone, that one doesn't have this missing a partner, it'll start falling off. But as long as you control that front end, you have really control of what the molecules do. So either we have proteins that help it, that break it, or that basically just give us a little filter, or like a little safety net, so it doesn't collapse. All right, let's see. Again, right, so here's the big key for cell division. This is what we're talking about. There are centrosomes. They basically end up being anchors on this side, which would be our minus side. The plus side, which is the fast growing end, is the one where it'll literally try to make these microtubules, send them out. And this is depending on what they go and find, right? Some of these are going to go, they're going to go interact with our chromosomes, and then they'll be stabilized with that interaction with the kinetical, right? Other ones, they'll grow, they basically interact with the other ones from the other section here. And then what those are doing is like, you're setting up two of these straws like this. And we're now going to show you how we're going to zoom in to see how the molecules move across this thing. And with that, we can actually make a force to push these things away. So for these guys, we have these really cool players called microtubule motor proteins. I remember the first time I was learning about these, the only way I got to remember them was like I imagine like it was actually myself doing them. So we have two types. We have dynein and we have kinesin, right? For this thing, the big thing is that they each walk on the microtubule, but they go their own direction. So our kinesin is going to be going towards the plus end, our dynein is going to our negative, right? So it literally like grabs like onto that tubulin and it like clamps onto it. It has the other little foot move forward, grab onto the next one. As it's doing that, we're actually going to be burning off energy from ATP. So every little step they're taking is ATP, hydrolyze it, release the ADP. Then it basically releases, the other leg moves forward, that one steps in, and we have to burn ATP one more time, right? So every step it takes on that thing, it'll move itself across, burning ATP. So it's super cool. So that'll be on the top side, hitting the microtubules, and then on this side, basically it's the places where we have interact with different things, right? They interact with the proteins. This will be stuff that we either find it on vesicles, in the case of, when we're doing cell division, like this guy, is you basically have two of them clamped onto each other. Right? It'll be like this, the other one will be like that. When one of them was starting to walk towards the positive end, right, like the top legs would be walking like that, trying to go that way. These bottom ones are trying to go basically this way, like they're trying to go onto this cable going that way. That force ends up making them kind of go like this. The more he walks this way, that cable gets pushed further that way. This leg pushes the cable that way, right? By having two of them be in the opposite side. At that point, you're doing this to the cable. They get pushed apart. That's what physically pushes your cells. Does that kind of make sense or no? I'll put a nicer drawing about it, but it's like if your cable's like this, these legs, if they're walking this way, the cable's feeling the mechanical force that is getting pushed that way. Right? So it's like as I'm going through here like this, if I walk forward, like I'm pushing the cable that way, so it moves that way. On the opposite side, you have the other two legs, and they're chasing the same thing. They're trying to go that way, but as it moves forward, you can see I move the ruler in the opposite direction. So by doing this, that same thing, they're both walking the same direction, you actually push the cables apart. So that's pretty cool. That's the next one.
Which one does that? Kindison?
This one, I think it's the positive. I think it's Kindison. I need to double check my notes on that guy. Yeah, I'm gonna find you a nicer picture and I'll zoom in and I'll put this little drawing onto it. The other thing we care about is like we're saying, moving organelles or vesicles, and those is use these side chains down here to basically be the connectors. There's something proteins on the vesicles themselves, you do that protein-protein interaction. Again, in my head, I think about those are those secret handshakes where they know how to grab onto each other, super high affinity. And then this molecule will literally walking across the microtubule, dragging that bubble along with it, giving us these really cool drawings like that. So the cool thing is like, if you want to send something away from the cell, right? Kind of like this. We're trying to send something away from the cell, then what you do is you're going to bring in a kinesin, right? And this is going to grab that vesicle, drag it out towards the positive side. If the opposite thing, you have something, you want to bring it into the cell, you put it onto the diamine, now it's going to walk the other way and get it constantly inside the cell. Yeah. All right, cool. So in this one, again, the way I remember it was like, I was thinking about it like it was my legs. Green one will be your right foot, light green one is basically your left foot, right? These are the ones that are going to be almost like snowshoes. I don't know how to imagine them, but like cleats. They're like dug into that microtubule super well. They're grabbed into it, right? So the ATP tightly bound, that means you have a grip. And then what's going to happen is the ADP becomes loose. So in that case, it'd be like, if I'm in this conformation, this is my ATP. When you release the ADP leg, that one becomes loose. Now you have the chance to kind of can wobble, and it has the ability to kind of bend, and that's what lets it move forward to grab onto that next step. Right? When it's doing that, ATP, I don't listen to trading yet. What can these YouTube it then? All right, so you can see here, now that exchange ADP to ADP. So it's like, that's the kind of way that they like reset themselves. So we're going from that low energy, now we're bringing in the high energy molecule. And then this would kind of gives it the grip of like, you're switching between legs, right? So it's like, now this leg matter, this the one is grabbed on, the other one kind of lets go, and it has a chance to kind of grip forward. And every time you're doing this, you're burning the ATP to power us up, and also the confirmation of what leg you're grabbing on. And that's what keeps you just walking in one direction. That kind of make sense? Yeah. Let me see if I can find a video of this one for you guys. So there, big thing story, right? Summarizing all this together is microtubules, they look like straws, right? That straw, we can collapse it from the top of the straw in. It normally does a lot faster on the positive side. That reaction of building itself and falling apart. It's a lot slower on that side. We can control it. One, we can bring in a bunch of GTP, this thing will grow forever. If you bring in a bunch of GDP, this thing will fall back and completely collapse on it, right? The other ways we can kind of control it is we can bring in proteins that help modify it. Either they can bind to the 5' end and make it more stable, aka, or help us polymerize the reaction, making this go faster. Or you can bring stuff that helps hydrolyze things and break it down, and then we collapse these cables. The other one is the collapse, which basically gives us a little bit of a safety net. It could be going, collapse a little bit. We have the cap proteins. Now that we have the cable set up, the cool thing about it is we can use these motor proteins that go in specific directions, and either we can attach things to them, like other vesicles to move stuff, or we can attach them to themselves to make the microtubules really give us mechanical force on the inside. Yeah, all right, cool. Any questions? No? All right, I think we're good for today. And I'll see you guys on Friday.
Thank you.